I'm going to go over the gas law review packet, chapter 10. We're going to do problems 30 to 41. I'll start with number 30. Okay. Which of these gases will behave most ideally? Now, to be an ideal gas, you have to have minimal interactions and you have to have a minimal volume. So you have water, carbon dioxide, helium, SO2, and H2S. What you're looking for is the simplest gas molecule, and the simplest one would be helium. Helium would have the least interactions. Helium would be the lightest gas, so it would have the least amount of interactions. So this is just based on helium being the simplest formula. And an atom would be a most ideal gas as opposed to a molecule. All right, in the next one, 31 to 34 are going to refer you to this chart. Okay, and the first question is going to be, which one has the greatest number of particles? One thing I'm going to notice about the chart is everything's at 25 degrees. So your kinetic energy for each one is the same. Temperature is a measure of kinetic energy. Okay, the volume is constant. Okay, and then as far as which one has the greatest number of particles, it doesn't depend on the identity of the gas, so the molar mass wouldn't be in place here. Now, the basic gas law, if I go to the universal gas law, combined is P1 V1 over T1 equals P2 V2 over T2. That derives down from PV equals nRT. If I divide both sides by N and T, that gives me R. And to make the combined gas the universal, all I have to do is put moles back in, and moles would go on the bottom. So that is the gas law if you're including moles as being a variable. Okay, and that's what's happening here. The volume and the temperature are constant. It's a gas law we haven't discussed. P1 over N1 equals P2 over N2. Okay, in that case, the one with the greatest number of particles, if the particles go up, so pressure over N is a constant, so the greatest number of particles is represented with the greatest pressure, and that would be gas A. Okay, which one's the fastest moving? I can look at kinetic energy equals 1/2 the mass times velocity squared. If you use this equation, mass is measured in kilograms, and as your mass goes up, your velocity goes down, because Ke would be a constant. In this case, the temperature doesn't change. But if your mass goes down, your velocity is greater. So the one with the lowest mass would be the fastest. Okay. You also see that if I do the equation for URMS. So if I do URMS speed velocity, it's the square root of 3RT over the molar mass. R and T are a constant, so which one has the greatest velocity? The lower the mass, the greater the velocity. So both those equations point to the one with the lightest molar mass being the fastest, and that would be helium, C. Okay, and that's 32. Let's see. All right. Which one has the greatest average kinetic energy? Well, they're all at the same temperature, so all have the same kinetic energy. If you were to look at the individual particles, some will move slow, some particles will move fast, but on average, that's what's represented by the temperature. So the average would be the same. Which one has the greatest density? Okay, there is an equation for density, but I would just prefer everyone to know that density equals mass over volume. And mass would be grams, and volumes would be liters. Now if I took PV equals nRT, I can get this equation by solving for N divided by V. So if I divide by V, That gives me RT. Okay, P over RT. Now, to turn the moles into grams, I would take the molar mass times the N over the V, and that would give me my density. Okay, and then I would multiply the other side by molar mass, so I get P times molar mass over RT. So the density, and that's the equation. I think you would be better deriving that than memorizing that. I don't think anyone would remember that by memory a year from now, but you can always know how to derive it from PV equals nRT. R and T are constant in this equation, so basically I want to look at each one and find pressure times molar mass. So going up here, 2 times 17, A would be 34. 1 times 40, B would be 40. And 1 times 4, C would be 4. So the one with the greatest density would be B. Okay, the greatest molar mass and the greatest pressure combined. Okay, so the answer to that one will be B. The reason I'm going over this is none of these questions are going to be on a test. These are higher level questions, just designed to make you think, and they're kind of in the style of an AP test. But I left it on there just because I thought it would be good to do something a little higher level. Okay. Not going to do that one yet. Okay. That's 34. Okay, 35. There was a similar question to this on the review packet. I'm sorry, it was the study guide. And 35. It takes us step by step. What to note here is I have 4 moles in this one. I have 6 moles of gas in this one. And this one has 4 plus 6 for a total of 10 moles of gas in the total. Okay, what's the ratio of moles from hydrogen to argon? Okay, respectively. The ratio would be 4 to 6, which reduces to 2 to 3. So my answer here is 2 to 3 is the ratio of helium, hydrogen to argon. This is kind of like an AP question. They kind of guide you through what they might ask you initially and have you do each step individually. Okay, if the pressure of hydrogen in the first vessel is 2, what's the pressure of argon in the second one? So the pressure here is 2 atms, and this is pressure, this is volume. So this is really, and this is moles. Okay, the volume is constant, 1 and 1 from 1 to 2. So what I'm going to look at is I'm going to look at the relationship between pressure and moles. So it's going back to that last equation I used. Pressure 1 over N1 equals pressure 2 over N2. Okay, so I can do this mathematically, and that can be derived from the universal gas law. And so I'm solving for P2. So P2 would equal P1 over N1 times N2. And so just plugging my numbers in, I get 2 atms divided by 4 particles times 6 particles. Without a calculator, everyone's so used to a calculator. Well, 2 divided by 4 is 2, so the answer is 6 divided by 2 is 3 atms. Okay, and now getting to the next question, they're now going to expand the gas and combine the gas. So you have 2 laws going on here. The first one would be Boyle's law. P1 V1 equals P2 V2. So I would see an expansion of the gas. Okay, if I solve for P2, it would equal P1 V1 divided by V2. And then very simply, V1 is 1 liter, V2 is 2, so everything's going to be divided by 1/2. And the initial pressure of the hydrogen was 2 atms. So the answer for the hydrogen is that your pressure equals of hydrogen 1 atm. Okay, the same thing. I knew the pressure here for number 2 I found in this previous problem was 3 atms. And again, it's going to be 1/2 times 3, so the pressure of the argon is equal to 1.5 atms. And then you're going to use combining these, you're going to use Dalton's law. Pressure total equals pressure of the hydrogen plus the pressure of the argon. So you're going to add 1 atm plus 1.5 atms, and in the final, your pressure total is going to be 2.5 atms. And now my answer that best fits is going to be A, 1 to 1.5 to 2.5. Okay. This next question is a lab. You know, if we're still in school, this was always a fun lab to do. We would do a reaction where we would put magnesium metal into hydrochloric acid. What you produce is magnesium chloride plus hydrogen gas. So you're generating a gas. We'd have a solid, we'd have aqueous, and we would have aqueous magnesium chloride. You could do it as an anionic equation, just showing H plus and Mg plus 2. And this would be a 2 as a ratio. Okay. In our lab, we would find the mass of magnesium, and we'd use dimensional analysis to find the moles of hydrogen. But what they want you to find is the molar volume of a gas at STP. Now, I wouldn't expect you to, this problem is, you know, I wouldn't be expecting this problem. It's a high-level problem. At STP tells you a lot of interesting things. It tells me that the pressure 2 is 760 atms, and it tells me that my temperature 2 is 273 K. So those are my final conditions. Okay. As usual, I want to define what I want. I want the molar volume of the gas. So I want to know the number of liters of hydrogen divided by the moles of hydrogen. Now, because I have grams of hydrogen, I can find moles real easy just by dimensional analysis. 0.0052 grams of hydrogen. I'm going to convert grams to moles, and it's 2.02 to 1. My answer is going to have 2 sig figs in it. So when I do that, I get 0.0026 moles of hydrogen. So this is 0.0026. A little tricky on the problem because there's a lot to think about. First of all, you have the liters given as 61 milliliters, and you have a pressure of 747. Okay. What it didn't take into account is this is collected over water. So this is telling you the pressure of the hydrogen gas. Because actually, if you did this lab, you'd have to take into account the vapor pressure of water and subtract it from your air pressure to get the actual pressure of the hydrogen. But they skipped that step and they just gave you the pressure of the hydrogen, 747. The thing that we have here is we have pressure 1 equals 747 millimeters of mercury, or you could call that a torr. Volume 1, now I'm going to take that 63 and convert it to liters, because in the end I need liters. So right now I'll take milliliters times liters, 1 to 1,000. So volume 2 ends up being 0.0613 liters. And temperature 1, and this is hard, this is what makes it hard. It just mentions STP up here, but here it's telling you that it's 28 degrees. Well, 28 plus 273 gives me 301 Kelvin. So what I have to do is I have to plug in everything into the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And I'm going to push this up and make sure that you're seeing this. It's tough for me to see what's on video. Okay. What I'm now going to do is correct for the volume. there's no way this problem would be on the test. This would be a challenging problem. V2 equals, it's an AP style problem. You would see a problem like this on the AP test. V2 equals P1 V1 T1, and then multiply this side by T2, divide it by P2. So you got T2 over P2. And what I'm doing is I'm applying the gas laws to a lab. Okay, and this would be your lab calculations. Pressure 1 is 747. All the units are going to end up canceling out. The pressure initially, V1, is 0.0613 liters. And then I got T1, T2, which is 273 K. I'm then going to divide that by T1 and P2. So T1 is 301 K, the K's cancel out. And pressure 2 would be 760. And millimeters Hg would end up canceling out, which I kind of ignored up there. I'm left with liters, running out of space. The volume 2 corrected would equal 0.0546 liters. Now, right there with everything, I'm good for 3 sig figs. So I'm going to take 0.0546, but I'm dividing that 0.0026, and here comes my answer. I'm going to plug that answer in, and then the molar volume ends up being 21.0, not a 0.0, just 21. So you really shouldn't see a 0.0 because that means there are only 2 sigs. So liters per mole. We did this lab, and when we do this lab, you get what you actually should be, your value actual should be 22.4. And a lot of students get close to 22.4 when they actually do it. But the answer we're looking at is D. Okay. Backside, number 39. Let's get that recentered. Okay. Basically, this is Boyle's law. You have a constant temperature, so it's P1 V1 equals P2 V2. Okay, and so you're trying to find out what the final pressure is. So pressure 2 equals P1 V1 divided by V2. And what you know is your V2 equals 500. Your V1 equals 1,000. And your P1 doesn't really, well, it says at STP, so you know P1's 1 ATM. But your factor that you're going to multiply your P1 by is going to be 500. No. 1,000 divided by 500, which is a factor of 2. So pressure is always going to go up by a factor of 2. So your pressure will increase by a factor of 2, and that shows Boyle's law. Okay. These problems tend to be confusing. They take 2 volumes. This represents a valve, so you have it cut off. Okay, I have nitrogen gas here, I have oxygen gas. Nitrogen gas is 28 grams per mole. Oxygen gas is 32 grams per mole. Okay, what do I know about it? I know that the V1 is equal to 4 liters, and P1 equals 6 ATMs. Over here, I know that my initial volume, V1, equals 2 liters, and pressure 1 equals 1 ATM. This is going to be a combination. First, you're going to apply same law, Boyle's law. It's happening at a constant temperature, okay? So for each one, we can say, well, P1 V1 equals P2 V2. And we're going to do these problems as separate, 2 separate problems. So I want to find out what the final volume is, which I know. When I open this valve, the final volume is 4 plus 2. So it's going to go to 6 liters. Okay, so what's the pressure? Well, it's the same equation here. Pressure 2 is going to equal your pressure 1 times V1 over V2. Okay, and so you got 4 times 6 divided by 6. So your answer is going to be 4 ATMs for this side. For this side, P2 equals P1 times V1 divided by V2. So I have 2 times 1 on top, and the V2 is 6. So I end up with 2 divided by 3, which is 0.3 liters, or 0.33. So that's going to be my final pressure on this one. So V2 equals 6, P2 equals 0.3. And then finally, the fact that you combine them means that the pressures then add up. Okay? I know the pressure independently of the nitrogen. That's the part. This would be the partial pressure of the nitrogen. This would be the partial pressure of the oxygen. Put together, P total will equal the pressure of the nitrogen added up to the pressure of the oxygen. And so basically it's 4 plus 0.3. So your answer is P total equals 4 ATMs plus 0.3 ATMs. So the answer is 4.3 ATMs. The answer is B. They didn't really pay attention to sig figs because I guess technically you could say that 0.3 was insignificant, but they're not paying attention to sig figs. All right. Initially, I was looking at the molar masses because I thought this problem might be a Graham's law problem, which the next one is. Okay. This next problem is Graham's law. You have gas X being 32, you have gas Y being 2. And anytime you have a problem that's Graham's law, you want to write down Graham's law, which is rate of X. Now I'm going to put Y on the top because it's the lighter, it's the faster gas, divided by the rate of X. That's going to equal to the square root of their molar masses. So I end up with the 32 on the top, grams per mole. I end up with 2 on the bottom. And it's a lot easier to look at it this way. 32 divided by 2 is 16. The square root of 16 is 4. So gas Y is going to be 4 times faster. So if gas Y goes 1, 2, 3, 4 and gets to 6, gas X would only get to 1. Okay, and the answer is, where do they come together? Okay, so in the second, if I let it go further, if the two gases are advancing, this will go 1, 2, 3, 4 and get to 2. Then this reaches 2, and that tells you that your answer is point A. Because the ratio will be 4 to 1, and this would have traveled 8, this would have traveled 2, and 8 divided by 2 is a ratio of 4 to 1. And that's it. I wouldn't particularly worry about any of these for the test, but now you know how to do them. And separately, I'll give you the answers to 1 through 29.